Okay, now problem number 2 on the test, also worth 20 points, is shown here. In this case, we have a closed system. It's a piston cylinder that contains a binary mixture of 10 kilograms of nitrogen and 10 kilograms of oxygen at an initial mixture temperature of 300 Kelvin and a pressure of 1,000 kPa. Heat is transferred isobarically, same pressure, from the system while the mixture reaches a new temperature, a lower temperature of 250 Kelvin. You are to determine the heat transfer from the system, assuming, first of all, ideal gas behavior, and then redo it for real gas behavior. Okay, so this particular problem is a closed system. It is a closed system with a binary gas, and so it's just a simple process going on. It is not a mixing problem because they're already mixed. And so what we do have to assume is that we have a gas mixture that's binary in nature, and we're first of all going to look at the ideal gas version and then the real gas version. And so we'll select the ideal gas one first. We'll come in here. Again, our initial state is going to be the state of having nitrogen as gas A, and oxygen as gas B. And our first state here, we can say that the amount of mass that is in is 10 kilograms and 10 kilograms. And so we see that the mass fraction is 50%. So it defaults, or it's already at a 50-50 binary mixture of that particular two components. We know that the temperature is 300, and we also know that the pressure is 1,000 kPa, or 1 megapascal. In this particular case, we know the mass, the total mass. The total mass is equal to 20. All we did was, when we specified the percentage, it was just the relative percentage. But now that we know the mass, total mass, we see that it's 50% of nitrogen, 50% oxygen. And so this tells us that the vessel initially is 1.67 in size. Volume-wise, it's a closed system when it's at this temperature and pressure. And so what we're going to be doing is going to a second state, and the second state is when it reaches a temperature of 250. Again, the total mass stays the same, and the ratio, the mass fraction, is also the same. And we know that the volume, though, is going to be changing in this particular process. Okay, as it changes, once it reaches this temperature, we will also be able to determine the pressure. So at the present time, we don't have two independent thermodynamic properties in order to specify the final state. What we have to do is we have to go into the process panel, and we say, for this particular process, we're going from state 1 to state 2. And when we do that, we know that heat transfer and work is going to be involved. Okay, but what we also can say is that there is no shaft work. And so this term here is equal to 0. There is boundary work. And because we're not asked anything about the irreversibility, we really don't have to worry that much about the boundary temperature. And so this then is our our process panel that's occurring. We do a calculate here, and let's see, what am I not? And let's see, I'm missing something. What am I missing? Okay. We know specific volume of total volume, pressure. Oh, I'm sorry, I failed to read the problem fully. The process itself was considered to be isobaric, and so we do have the two independent thermodynamic properties associated with state 2. And so with that, we see that the volume went from 167 to 139. We did have the process panel here, and when we do the calculate here, which it already has, in going from this state to this state, two things are occurring. And the two things that are occurring is that there is work being done, and this is work being done on the system because the volume, the boundaries have gotten smaller, so we have this negative work being done on the system, but at the same time we are taking out of the system 967 kilojoules. And so it's the combination of these two in the first law that then gives us the change in the internal energy of the process. And so it's that then is answers the questions for this first part. So for the case of ideal gases, we see that the answer is 967 kilojoules. Okay, so now I'm going to go back and I'm going to redo this particular problem. And this time it is a simple process. And now we're going to assume it's a binary gas of real gas behavior. And we're going to then select this again with a nitrogen and oxygen. And it defaults to the 50% mass fraction as we expected. Our total mass is 20. And we also know that the initial pressure is 1,000, and the initial temperature in this particular case was 300. And so what this then allows us to see is that under the real gas behavior, at this pressure and temperature for this mixture, what we're seeing is it calculates the reduced pressure and the reduced temperature, and it calculates the compressibility factor, and the compressibility factor tells us that this initial state is very close to behaving as if it was an ideal gas. Okay, so we're now going to specify state 2, and we know that state 2 is the isobaric constant pressure. The temperature is 250. We once again have the same amount of mass, which is 50-50, and we now see that the reduced temperature is a little bit less because the temperature is a little bit less, and what we also see is that the behavior is such that it should be very similar to that of the ideal gas behavior. So what we now need to do is go to our process panel, state 1 and state 2, and we see that if we then do the calculate, we do see that because of the difference, the real gas behavior, we're seeing for this particular problem a certain amount of work that's being done during the compression process, and we do see a certain amount of heat transfer. And so in this case, we're seeing a heat transfer of 1,032, and so we are seeing about 60 or so additional kilojoules as we go from state 1 to state 2. From state 1 to state 2. State 1 in this particular case, assuming ideal gas, had a volume of 3.19. State 2, assuming real gas, had a volume of 2.91. So this particular problem, you can see that a slight difference in the magnitude calculated of the heat transfer and work when we assume non-ideal behavior.